In this video, we will consider how we can use power control to make a single-cell system as efficient as possible. And efficiency can be defined in different ways. If we are maximizing the sum rate, well, then we find the most spectrally efficient solution, and we will look at how to do that in the uplink and in the downlink and study its properties in a simulation example. And then we will define the energy efficiency as an alternative metric, and we will look at how power control is affecting it and how we can use beamforming and spatial multiplexing to also improve the energy efficiency. In the last video, we talked about that the effective SINRs that the different users are achieving depends on the power control coefficients of all of the users. And we have so far mainly been treating them as being constants, but in the previous video we were optimizing their values in order to achieve something that we call maximum fairness. And in general, there are different ways of selecting these coefficients that will provide us with different operating points that are good for different purposes. So for example, if we have two different users, then for user 1, its achievable rate is log 2 or 1 plus its effective SINR. And for user 2, it has a rate that is log 2 or 1 plus SINR2, which is the effective SINR of that user. And depending on our selection of the power control coefficients for these two users, eta 1 and eta 2, we can achieve different pairs of rates for the two different users. So there is a trade-off between them, which is determined by interference. And in the downlink, the trade-off is also determined by the power constraint, which is saying that we need to divide the power between the users. So some examples of operating points is the maximum sum rate, where we are maximizing the sum of the two users' rates, and it will end up somewhere at the outer boundary called the Pareto boundary of this so-called rate region. Another point is the maximum rate point, where the two rates are the same, which is also the same thing as saying that the two effective SINRs are the same. And in the last video we considered how to select the power control coefficients to achieve the maximum rate point. And in this video we will instead consider how we can select the power control coefficients to achieve the maximum sum rate. This will be the most spectrally efficient solution in the sense that we are transferring as much data over our communication channels as possible. However, there is no particular fairness perspective here. We don't really care about which user that is getting these data, as long as the total number of bits per second that we are transferring over our system will be as large as possible. In the short term, the maximum rate is providing the most fairness because everyone who is active in the system gets the same rate at the same time. While as you are moving around in the network as a user and you are gathering the data over time, and you figure out what is the average data rate that you're getting, well, that average will be maximized if you make the sum rate as large as possible at every given time. So one can say that maximum fairness is providing us with the short-term fairness, while by maximizing the sum rate we can achieve the largest fairness in the long run, because everyone will get the most data on the average over a long time as you're moving around in your system. So we will consider the sum rate maximization in this video and focus first on the downlink and then on the uplink. In the downlink, the optimization problem that we would like to solve is to find the power control coefficients that maximizes the sum over all of the users, and here are their rate. And the rate is log 2 or 1 plus the effective SINR of every user. And one thing that we have noticed previously is that the SINR expressions have a particular form, where in the numerator there is some kind of parameter, I call it AK here, multiplied with the power control coefficient eta k. So this is the signal term for user k. And if you are using maximum ratio precoding, AK is the number of antennas times the maximum downlink power times the gamma k, which is the estimation quality of the channel to this user. And if we're using zero force in precoding, well then AK is M, the number of antennas, minus the number of users, and then we're multiplying with the same factor again, rho downlink times eta k. Then in the denominator of the SINR, we have a noise term, and then we have BK, which is a parameter that is telling us how strong the interference is. And all the interference in the downlink goes through the channel to the user, so it's equal to rho downlink, the total downlink power, multiplied with beta k when we're using maximum ratio processing, while it's equal to rho downlink times beta k minus gamma k when we're using zero forcing. So we can notice here that the interference terms are smaller when we're using zero forcing as compared to maximum ratio, while maximum ratio is achieving a larger signal term instead. And this BK term is then multiplied with the summation over all of the power control coefficients. So this is the expression that we would like to maximize with respect to our power control coefficients. And we cannot just select any power control coefficients, because these are telling us how we are taking our total power and divide it between our users in the downlink. So the sum of these parameters should be smaller or equal to 1, where 1 means that we are using all our power. And eta k should also be greater or equal to 0, because we cannot allocate less power than 0 to a particular user. So this is our optimization problem that we want to solve. And first we will notice the following, that if we have some selection of power control coefficients, eta 1 to eta k, and we are considering another set of power control coefficients where we are for every coefficient multiplying it with some constant c, which is greater than 1, well then if we are putting it into the sum rate expression here, we are making the signal terms and interference terms larger by the same factor c, and they are then growing more than the noise term, which is a constant, which will lead to that every user will get a larger SINR. And the consequence of this is that if you give me any choice of the power control coefficients, then I can always increase all of them by the same factor, and I can do it to improve our performance. And if the original selection of the power control coefficients summed up to something smaller than 1, well then I can increase it by a factor so it becomes equal to 1. The conclusion from this is that at the optimal solution, where we are maximizing the sum rate, we must use full power, because if that weren't the case, well then we can always increase all of the terms by a factor c and increase the power. And that would be allowed to do. So we know that we should have maximum power. The sum of the eta k's should be equal to 1. And in this SINR expression, the sum of the eta k's is showing up in this interference term. So if we are replacing this with a 1, well then we should instead maximize an expression of this kind. The sum over the different users, log 2 of 1 plus a divided by 1 plus bk. And this factor here is independent of the power control coefficients, and then we should multiply that by eta k. And this turns out to be the same kind of problems as we were facing in an earlier video for the point-to-point MIMO channel, where we were dividing our MIMO channel into multiple sub-channels. Each of them contained a strength of the channel, which at that point was a singular value squared from the channel matrix, multiplied with how much power that we were putting on that sub-channel. In our case, it is this factor that is representing how good a channel is to a particular user, multiplied with which fraction of our total power that we are allocating to this particular user. But the problem formulation is mathematically the same, so the same waterfilling solution can be utilized. The solution to waterfilling power allocation have this particular form. The power control coefficient for user k should be the maximum of 0 or some parameter that I call mu minus 1 plus bk divided by ak. So this is the factor that was in front of eta k in the SNR expression, but upside down. And then we should select mu, which is a parameter, such that if we sum up all of the power control coefficients, we get 1. So essentially we can start with mu being 0, and then we can increase it gradually. until we get the summation here being equal to 1. So some properties that we can notice from this type of expression is that as we are selecting mu to have a certain number, then the larger the factor is in front of the eta k in the SNR expression, the smaller this upside down factor is going to be. So we will subtract the smaller number from mu, which means that if you have a better channel, you will allocate more power, have a larger eta k for that channel, which makes good sense. A user that has a good channel, we should take the opportunity to transfer with more power to this user so that we can utilize the good channel and transfer more data. Remember that we are not trying to maximize some kind of fairness, but to transfer as much data as possible. This also means that if some users have a very small AK divided by 1 plus BK, then this term will be very large. We will subtract a large number, and for the optimal mu this might be negative, and therefore we will allocate 0 power to this particular user. So with waterfilling power allocation, we allocate more power to users with good channels, and some users might not get any power at all. The reason that we call it waterfilling is that we can view the process of increasing mu until we are using all of the power as pouring water into a tank where there is an uneven bottom describing how good a channel is for the different users. So for user 1, who is the one with the best channel in this case, 1 plus B1 divided by A1 will be the smallest number, so we have the lowest bottom here. Then user 2 have the second best channel, user 3 has the third best, and user 4 had the worst channel. And then we start increasing mu, and after a while we start to add power to the first user. If we have more power, we are allocating to the second user, then to the third user, and in this example we are reaching the point where the sum of etas is equal to 1 before we have allocated any power to user 4 at all. So this is the way of solving the sum rate maximization problem in the downlink for a single cell system. And before we are making any simulation study of these results, let us switch focus to the uplink instead. So in the uplink, the sum rate maximization problem looks similar. We still would like to select eta 1 to eta k so that it maximizes the sum rate, which is the sum of the users. There is a log 2 of 1 plus the effective SINR. But in the uplink, the effective SINR is slightly different. So in the numerator, we have AK times eta k, so it looks the same as before, but AK have slightly different expressions for maximization and zero forcing. In particular, we have row uplink instead of row downlink. More importantly, in the denominator, we have 1, which is still the noise term, and then the summation over all the users, and now we have a parameter beta k prime, which is inside of this sum. This parameter is multiplied with eta k prime, which is the power control coefficient for the interfering user k prime, and this bk prime is describing how strong that channel is to the base station. Because in the uplink, the interference comes from the users. So the further away a user is, the lower the interference is going to be. So bk prime have either this form, row uplink times beta k prime, if we are using maximization processing, or it's row uplink times beta k prime minus gamma k prime if we are using zero forcing. So once again, the bk prime here is a smaller number if we're using zero forcing, but on the other hand we are reducing the beamforming gain when using zero forcing because we are throwing away some of the antennas, more or less, some of the antenna dimensions in order to get rid of interference. So the first difference between the sum rate maximization in the downlink and in the uplink is that these interference terms look different because the bk prime goes inside of this summation, which wasn't the case in the downlink. The second important difference is the power constraints, because now every user have their own total power, and we can vary between using all of it or nothing. So we can say that eta k should lie between 0 and 1, but there is no constraint here saying that we can move power from one user to the other one. We can only decide on who is transmitting with which fraction of its own maximum power. We will now identify a way of solving this sum rate maximization problem, and the first thing we notice is that the denominator of the SINR is the same for every user. So for the rate of user k, there is no k showing up here. So we always have 1 plus the summation over all of the users and then the bk prime eta k prime. To signify that the term is the same for every user, we define a new variable that I call s, which is 1 divided by this denominator. Then we will have a rate that reads log2 of 1 plus ak eta k s. Further, I will define a new variable, a new optimization variable, xk, which is equal to eta k times bk times s. And we introduce bk here just in order to get a particular form in our optimization problem. So if we are inserting now the definition of xk and s into this expression, what we actually would like to maximize is the summation over all of the users, log2 of 1 plus ak, which we have had all along. Eta k is now replaced with xk, and then since there is no bk here from the beginning, we divide with that term. So this is what we would like to maximize. Then we also need to keep track on that s have a certain relationship with etas or with x, and that we have these kind of power constraints as well. Our new problem formulation looks like this. We still would like to maximize the sum rate, but the sum rate is now expressed like this. We are not optimizing with respect to eta k, but x, 1 to x capital K. And we also treat s as an optimization variable. And our power constraints was before that eta k should be between 0 and 1. Now we express it as xk being between 0 and s times bk. There is also a relationship between x and s which is expressed in this particular form. This problem formulation is resembling the downlink problem, where we also had a similar thing to maximize, but we have more involved power constraints looking like this. So there is no simple solution that we can just write up directly, but we can notice, if you are familiar with convex optimization theory, that this is a convex optimization problem. Because what we would like to maximize is a function that is concave with respect to our optimization variables, namely x1 to xk. So the logarithm is a concave function, and logarithm of 1 plus a parameter here, xk, is a concave function. And if we are summing up concave functions, we also get a concave function. And we call it convex optimization because maximizing a concave function is the same thing as minimizing minus that function, and that function is convex. So we usually refer to this as convex optimization problems. And to obtain a convex optimization problems, these constraints also needs to be convex constraints. And in this case, we have linear constraints, which is a special case of convex constraints, because all of the constraints is involving our optimization variables just in a linear way here. Xk and s multiply with constants, 1 and the bk. And here is also like summing up the parameters, and it should be equal to 1 minus s. So we have two linear constraints. So the sum rate maximization problem is a convex optimization problem, and we can solve it with any convex optimization solver. We can of course implement something ourselves, but there is also off-the-shelf solvers that can solve any convex optimization problem. For example, something called CVX that can be utilized in MATLAB or in Python. Now when we know how to solve sum rate maximization problems in the downlink and in the uplink for single cell systems, let us revisit the simulation example from the previous lecture. So we were considering a circular cell with a radius 500 meters. In the center of the cell there is a base station with 100 antennas, and then we have 10 users that are uniformly distributed within this area. And uniformly distributed doesn't mean that the distance from the base station is uniform between 0 and 500 meters, but it's uniformly distributed over the area inside here. So there is actually more users in the outer part of the region than in the inner part, because there is more area the further out you are from the center of the cell. And some important assumptions is that we are considering independent Rayleigh fading, there is no intercell interference or anything, we are working at a carrier frequency of 2 GHz and we're using 20 MHz of bandwidth. And there are many other parameters that you need to define in order to run a simulation like this. I will use the same ones as in the previous lecture, so you can go back to that one if you would like to have the exact list of parameters. We start with the uplink, and we will compare 3 different types of power control. 2 of them were considered in the previous lecture as well. That was when we used maximum fairness power control, and as a benchmark we used full power on every user. So every user have eta k equal to 1. And now we are adding the maximum sum rate as one potential way of doing our power control. And here I'm showing the power control coefficient for a randomly selected user, and on the vertical axis I have the cumulative distribution function, which is saying that as I'm dropping the users randomly in the cell, I will get different power control coefficients depending on where the user is and where the co-users are in the particular drop of the users. So we have variations like this. We can see here that if we are using full power, then all of the users are all the time using eta k equal to 1. If we are maximizing the sum rate, then we get a red curve where 30% of the users are using less power than the full power, and the remaining 70% are using full power. And if we are considering maximum fairness, then only 10% of the users, namely 1 user per drop, is using full power, and the other users are cutting down their power to limit the interference. So it is typically the user with the worst channel that is transmitting with full power, and the other ones that are avoiding interference. So let us look now at the performance that the user are getting. First we consider the uplink per user rate. So if we consider a randomly selected user in a random drop of users, then there is a variations in megabit per second between the different users depending on where they are and where the co-users are. So it is once again a cumulative distribution function that we are showing here. If we are using maximum fairness, we have a rather flat curve here. In a given user drop, all of the users get exactly the same rate. But when we are dropping users over and over again, we will see rate variations because sometimes the users are more in the center of the cell and can get better rates, and sometimes you have users that are further out. Actually, most of the time you have some user that is close to the edge of the cell, and they are then limiting the performance for all of the other users. If we are using full power on all of the users, we get the blue curve where there are huge variations. We have users with very good performance, but we also have users with very low performance. If we are maximizing the sum rate, we get a red curve here, which is mainly to the right of the blue curve. But for the strongest users, the one with the best channels, we actually have the red curve being to the left of the blue curve. And being to the left means that you have lower performance. So what essentially happens here is that in order to maximize the sum rate, then some of the users in the center of the cell cut down on their power. Not as aggressively as you would have to do in order to get the same rate for every user, but enough in order to bring up the performance for the user at the edge of the cell. And we also see that the user at the edge of the cell don't get as high performance as with maximum fairness, but we find some kind of trade-off so that we are utilizing all of the users' data rates, but not to the extent where we are forcing everyone to get the same rate. And since we are maximizing the sum rate, then it's not the individual rates here that we are caring about, but the sum of the rates in every given user drop. And that is what we are showing in the figure here to the right with this uplink sum rate in megabits per second for all of the users in one drop of the users, and the randomness is that we are dropping the users over and over again 1,000 times, and we are computing the sum rate for every such occasion, and then we are ordering them here. So we are getting a cumulative distribution function. And we can see as expected that for every drop of the users, if we are maximizing the sum rate, of course we get the maximum sum rate, the largest one. So it's always to the right of all the other curves here. If we are transmitting with full power, we are getting the blue curve here, and if we are targeting maximum fairness, we get the black curve. The black curve is for the worst cases better than full power, but in other cases it is not as good as using full power. But here we really see the trade-offs, that if we are targeting maximum sum rate, we get the highest sum rate all the time. If we are targeting maximum fairness, we are guaranteeing that the worst case situations are as good as possible for our users. So in summary, sum rate maximization is based on the idea that we would like to maximize the sum rate by sacrificing the fairness between the users. And we can say that we are focusing on long-term fairness. As a user is moving around in a network, it will on the average get its fair share of the maximum sum rate that we get on the average. But in the short term, we might be in situations where we would have been better off with maximum fairness. If we now switching focus to the downlink, here I'm showing the power control coefficients that we were getting with maximum fairness, equal power allocation, and maximum sum rate. Since we have 10 users, equal power allocation results in 0.1 as the power control coefficient for everyone. With maximum sum rate, we get something that is similar to that one, but not identically the same. And with maximum fairness, we get a slightly larger variations here. If we are looking at the downlink per user rate for a randomly located user in a random drop, we can see that we get some different curves for different methods. With maximum fairness, we get as expected the best rate in the worst cases down here. If we are instead maximizing the sum rate, well then we are focusing the attention on the best users, the one with the strongest channels. Remember that we are using waterfilling power allocation here, so the better channel you have, the more power you will get. And that also means that the worse channel you have, the less power you will get, and that's why we have worse performance for the weakest users, but better performance for the user with good channels. An equal power allocation is rather close to the maximum sum rate case. And in particular, if we are now considering the downlink sum rate that we get in different drops of users, here is the randomness that we are considering different drops of users. We see that the maximum sum rate and the equal power allocation curves are very close together. Of course, maximum sum rate is always slightly better, but the difference is not that large. Of course, in a setup with fewer antennas or lower SNR to start with, there might be a larger difference between these methods, but here the difference is rather small. While there is a distinct improvement in sum rate over maximum fairness if we are targeting maximum sum rate. So, sum rate maximization is similar to equal power allocation, and we are once again sacrificing performance for the user with the worst channel conditions in order to bring up the sum rate. Let us now switch focus and consider another way that we can consider an efficient power control. So far we have considered power control that is maximizing the sum rate or the spectral efficiency. But efficiency could also be defined in terms of what we call energy efficiency. So in general, when we have some kind of system that we are analyzing, one can make a benefit cost analysis. In our case, we have a communication system, and the benefit of that system is that it produces a data rate in bit per second. That is the service that we're delivering to our users. And the cost that we're having, at least one of the costs, is the energy consumption, the watt that we are consuming when we are operating our system. And watt is also joule per second. A benefit cost ratio can then be created by taking the benefit and divide with the cost to try to figure out what is a good balance between these two different things. And if we divide the data rate by the energy consumption, the data rate is in bit per second, the energy consumption is in joule per second, and this per second here is cancelling out each other, and we get a unit of bit per joule. And this is what we call the energy efficiency of our system. And why are we caring about energy efficiency? Well, one thing is environmental concerns. If we are consuming energy, typically the energy production of the day is mainly non-renewable and creates pollution. So as long as that is the case, we should try to keep down the environmental impact and keep down the energy consumption. So if we are designing an energy efficient system, then for every joule of energy we can transfer as many bits as possible. Another type of concern will be economical concern. So the energy price is something that every operator of a network needs to care about. And we can express the energy price in joule per euro or joule per dollar. And if we are multiplying the energy efficiency metric here with joule per euro, we will get bit per euro instead. So the whole thing will turn into a cost efficiency analysis, but essentially the same thing. If we are making the energy efficiency as large as possible, then for a given energy price, we also make the system as cost efficient as possible. Then if we are talking about cost efficiency, there might be other types of cost than only those ones that are related to energy consumption. But once we have transferred this into a cost efficiency in bit per euro, we can also add other types of costs that are not directly energy related into the benefit cost ratio as well. But we will not do it in this lecture. So to give you an example of the energy efficiency of base stations of the past, such as 4G base stations. Here is an example of a base station. This is a site with 3 different base station sectors that are transmitting in different directions. So we have 3 antenna panels pointing in different angles, and they are supposed to cover 120 degrees each. And underneath these base station antennas, there are power amplifiers. And these ones are consuming a large amount of energy. There is a paper from 2011 called How Much Energy is Needed to Run a Wireless Network. And for this entire site here, the energy consumption was at that time 1.35 kilowatt. And this base station site could transfer up to 28 megabits per second. If you are computing the ratio between the two different numbers, so 28 megabits per second divided by 1.35 kilowatt, we get the energy efficiency of around 20 kilobit per joule. So this was how a 4G base station were performing in terms of energy efficiency. But we can design our system in a more energy efficient manner, and we can also select to not utilize the highest data throughput if we don't need it, in order to bring up the energy efficiency as well, and at the same time lower the energy consumption at a particular point in time. There are 3 main sources of energy consumption. There is the power amplifiers, which are creating the radiated signal. There is the radio transceivers that are creating the analog signal that is then amplified by the power amplifiers. And then there is the baseband processing, where we are processing the signals that are received and that are transmitted in the digital baseband. And all these 3 components are contributing to the total energy consumption, which means that we need to create a model of the energy consumption that are capturing all of these different categories. So we will now consider how we can use power control to get an energy efficient operation. And we will consider an uplink point-to-point system where a user device is transmitting to an antenna panel like this at the base station. And remember that the energy efficiency is measured by taking the data rate and divide with the energy consumption. And now we will put in some equations for this. So the data rate is the bandwidth multiplied with the spectral efficiency, which is log 2 or 1 plus this kind of signal to noise ratio. So we have the transmit power, I call it PTX here. There is the path loss or channel gain beta, and then we divide with the noise power, which is the bandwidth multiplied with the noise power spectral density. When it comes to the energy consumption in the denominator, of course the transmit power is one of the sources of energy consumption. When we are transmitting with a certain power, there is typically a large loss in the power amplifier, here described by mu, which is the amplifier efficiency, which might only be 25% or 0.25. So by dividing with this number, the actual energy consumption of the power amplifier is larger than the transmit power. In addition to that, there is many other components that are consuming energy. I call it here P circuit or circuit power, and this could be all of the base stations, digital baseband processing or the analog processing and filters and everything that is needed in the baseband unit and in the radio unit. To give you a sense of how the energy efficiency is behaving, we will now fix all the parameters except the transmit power and the circuit power. To the bandwidth, we are assigning the 10 MHz number. For the power amplifier efficiency, 0.25. And if we take B times N naught divided by beta, so we take this term here upside down, I will let it to be 0 dBm. In the graph here, I'm showing the energy efficiency in megabit per joule along the vertical axis, and I'm changing the transmit power, PTX, in dBm. So this is decibel on milliwatt. If the circuit power is 1 watt, so this term is 1 watt, we can see that the energy efficiency is increasing up until a certain point here, and then the energy efficiency starts to go down again. And the maximum value is happening here around 20 dBm, which is 100 milliwatt. And if we multiply that by 4, because we have 1 divided by mu, then we have something that starts to be a number close to 1 watt, or half a watt at least. And that means that this term here starts to be around the same size as the circuit power term. And that is when adding more power will of course increase the data rate, but also have a substantial increase of the energy consumption here. And since the energy consumption is increasing in a linear way with the transmit power, while we have a logarithmic behavior up here due to the logarithm and the PTX being at the inside of a logarithm, that means that after a certain point we will always have the behavior that the function is going down again. And this is called a unimodal function, where we can control the transmit power so that we're operating at the maximum number here. If the circuit power is larger, which it might definitely be in reality, say 10 watt, then the maximum value is at a higher transmit power, because if this term is larger, we can use a higher power before the term here becomes comparable to the circuit power and therefore is a limiting factor. So if we have a high circuit power, we can also use a higher transmit power. But of course the energy efficiency is going down, because now we are both consuming more energy in the analog and digital circuits and in our power amplifier. And if we increase the circuit power all the way up to 100 watt, well then we can also use even more transmit power. But after a while we will still enter the regime where adding more transmit power doesn't really help us very much, because the logarithm is a very slowly increasing function at high SNR. But the key point that I want to make here is that modeling the circuit power accurately is very important in order to identify the right energy efficient power control. So if we are changing here between 10 or 1 or 100 watt, well then we get very different solutions here. Remember, this is logarithmic scale. So a 10 times difference here can increase or decrease the transmit power by 10 times as well. Let us now have a look at how beamforming is affecting energy efficiency. So we will now consider a SIMO system, so we have multiple antennas at the receiver side, namely at the base station, and we will use the rate expression that we have been obtaining, the capacitor bound with maximum ratio processing. And since we only have one user, there is no particular indices here. We're using maximum ratio processing, so the effective SNR looks like this. We have M, we have row uplink, we have gamma, which is the estimation quality of the channel, and then we have the noise, and we have the self-interference here because we have imperfect channel knowledge at the receiver side. And remember that row uplink is essentially the transmit power divided by B times N naught. So this is some kind of transmit SNR. So when we are changing the transmit power, we are changing row uplink as well. And row uplink is also making it into gamma. So the estimation quality is also dependent on what the transmit power is. When it comes to energy consumption, we have the energy consumption in the power amplifiers. We have the circuit term that I was describing earlier, representing analog and digital circuits in the radio and in the baseband unit. But now I will also explicitly add a term here that is scaling with the number of antennas at the base station. So number of antennas multiply with P antenna. If we add one antenna, this is the additional energy consumption due to having more radius and having more baseband processing. And let us have a look at what will happen. Now I still have the same parameter values as before, but I assign P circuit to be 10 watt and P antenna to be 0.1 watt or 100 milliwatt. In the curve here, I'm showing the energy efficiency in megabit per joule as I'm changing the transmit power. And there are 3 curves. The red one is with 1 antenna, the blue one is with 8 antennas, and the black one is with 64 antennas. We can see that the optimal transmit power is roughly the same for all these curves, but the position along the vertical axis is very different. So the maximum is achieved with 8 antennas. We have a certain beamforming gain there. So we can see that the benefit from the beamforming gain is improving the energy efficiency a lot. So by adding more antennas, we are increasing the effective SNR, but we also are increasing the energy consumption in the denominator. And then we have once again this effect that the increase in the denominator is linear with the number of antennas, while here in the data rate term we have the logarithm of something that is growing linearly with the number of antennas. So after a certain while, adding more antennas will not be beneficial for energy efficiency anymore. And this is what we see here as well. With 64 antennas, we are down at the same energy efficiency values as with 1 antenna. So the conclusion is that the beamforming gain can help us to reduce the power that we need in order to deliver a certain data rate, or we can get a substantially higher data rate without having to increase the energy consumption very much, as long as this term here, that is scaling with number of antennas, is rather small compared to the other terms. And this is really because the received power is what matters, and the received power is proportional to the number of antennas multiplied with the transmit power. Finally, we will also consider how the spatial multiplexing of users is affecting the energy efficiency. So we consider the uplink of a massive MIMO system. The data rate will now be the sum rate for k users, and for simplicity we assume that every user have the same channel quality, and we will have the same notation as on the previous slide. So data rate is the bandwidth multiplied with log 2 of 1 plus the effective SNR of a particular user, which is the number of antennas times rho uplink times gamma, divided by 1 plus rho uplink times beta, but now we have multiplication with k because we have k users that are creating interference. So that is the bad thing with having many users, but the good thing is that we are multiplying with the number of users in front, because we are summing up the rate for every user, and this is the rate of one user. When it comes to the energy consumption, now every user is transmitting with the power PTX. So k times that number is the actual transmit power that we have in total, and we should divide that number with the efficiency of the power amplifiers on different users. We have a circuit power term again, and I have assumed that this one is at the base station, so it's something that doesn't scale with the number of users. And then the power consumption that is scaling with number of users is this term here that has to do with the number of antennas, both at the base station and the number of users that we have active. So m plus k times p antenna. This is the power consumption of adding an antenna at the base station or adding a user, which also is then associated with antennas. We will now continue the same example using the same parameter values, the same bandwidth, amplifier inefficiency, the channel parameters here. The circuit power is still 10 watt, the power per antenna is 0.1 watt, and the new assumption is that we have 64 antennas, so this is a massive MIMO type of system. And here is the energy efficiency in megabit per joule as I'm changing the transmit power per user, and we are considering 3 different number of users. The red curve is with 1 user, the blue curve is with 5 users, and the black curve is with 10 users. What we can notice here is that as we are adding more users to our system, we also get a more energy efficient operation. And every user is also transmitted with a lower power at the maximum energy efficiency. So why does spatial multiplexing of users lead to a more energy efficient operation? Well, if we look at our energy efficiency expression, we are multiplying with the data rate with the number of users, the power here, and also the power per active user. But the dominant factors in the energy consumptions are typically these terms that are not dependent on the number of users. The circuit power that is consumed at the base stations just for it to exist, for it to have all of its baseband processing units turned on, for example, and also the cost for having all of its antennas. And by having many users that are active, all of the other terms are growing. So by multiplexing several users at the same time and frequency using massive MIMO, we can have a more efficient use of our base stations. Yes, the energy consumption will grow because we add more users, we add more antennas, but the data rate is growing even faster, and that is why we get a higher energy efficiency when we are serving many users than when we are only serving one user and having one antenna, for example, that we were considering on the previous slide. So massive MIMO can improve the energy efficiency if we are combining it with also an efficient power control, where we are selecting the right power for every user in order to make the energy efficiency metric here as large as possible. In summary, we can use power control to make a communication system as efficient as possible. And we can either define the efficiency in terms of spectral efficiency or energy efficiency. For spectral efficiency, we would like to maximize the sum rate among the users. In a downlink, that boils down to a kind of waterfilling power control. And in the uplink, we need to solve a convex optimization problem to find a way that we should let the users control the powers to maximize the sum rate. We can also use power control to make the system as energy efficient as possible. And energy efficiency is computed by taking the rate and divide with the total energy consumption. And the energy consumption is both the transmitted power and the power dissipation in circuits. And how we are modeling the power dissipation in circuits is very important in order to find the most energy efficient solution. And we saw that when we are playing around with beamforming or spatial multiplexing of users, we can increase the energy efficiency by finding the right number of users, the right number of antennas, and the right power control to operate the system as energy efficient as possible.